A newly identified 1,000-kilometer fault buried deep beneath Alaska is suddenly coming alive, lighting up seismic sensors in places that were once considered quiet. Scientists are scrambling as fresh data reveals dangerous stress building along a structure few people even knew existed. This isn't a coastal megathrust. It's not the famous subduction zone. It's inland, remote, long overlooked. But if even a segment of it ruptures, it could unleash a magnitude 7 or larger earthquake, powerful enough to send shockwaves across North America. And here's the twist. Hidden along this very fault lies an extraordinary geological discovery of staggering value, one that could reshape how we view this entire region. So why are experts quietly reassessing this so-called sleeping giant? And what happens when it finally moves again? Stretching for nearly 1,000 kilometers, running from northeastern British Columbia across the Yukon Territory and into central Alaska, is the Tintina Fault. It is a right lateral strike-slip fault, meaning one side of the land moved to the right over time, similar in motion to California's San Andreas Fault. What makes the Tintina Fault remarkable is its immense scale. Geological evidence shows it shifted parts of the continent by roughly 400 to 500 kilometers. Entire crustal blocks and mountain belts were dragged vast distances, reshaping western North America. Most of this movement occurred about 90 and 40 million years ago, during intense tectonic reorganization along the continent's western edge. As plates collided and adjusted, the Tintina Fault absorbed much of that sideways strain. It also marks a boundary between ancient North American rocks to the north and younger terrains added from the Pacific to the south. At the surface, its trace appears as the Tintina Trench, a long, straight valley formed by structural weakness and erosion. Though major motion ended millions of years ago, deep fractures remain, and as a massive zone of weakness embedded within the continent's tectonic framework, the fault still has the potential to generate powerful earthquakes. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. Unlike southern Alaska's highly active subduction zone, the Tintina Fault has not produced well-documented large historical earthquakes in recent centuries. Compared to the powerful earthquakes generated along the Aleutian megathrust, the Tintina region appears relatively quiet. However, quiet does not mean inactive. Interior Alaska still experiences moderate earthquakes driven by ongoing interaction between the Pacific and North American plates. A striking example is the 2002 magnitude 7.9 Denali earthquake along the Denali Fault, a massive strike-slip rupture that redistributed stress across large portions of the state. In tectonically complex regions, large ruptures like this can alter surrounding stress fields and increase pressure on neighboring structures, especially ancient shear zones that remain mechanically weak. The Tintina Fault lies within this broader stress environment. Although it is not currently accumulating strain at rates seen along active plate boundaries, it remains a 1,000-kilometer zone of structural weakness. If another major rupture were to occur on nearby major structures, such as the Denali Fault or segments of southern Alaska's plate boundary, stress changes could theoretically influence segments of the Tintina Fault. Reactivation would not require continental-scale motion. Even limited slip along a portion of its 1,000-kilometer length could produce a strong regional earthquake. There is no evidence that such a rupture is imminent, but geological history shows that ancient faults can awaken under modern stress. Tintina may be largely dormant, but dormant is not the same as extinct. Just when the story seems to be about earthquakes, Tintina reveals something far more astonishing. Running almost parallel to this 1,000-kilometer fault is one of the richest gold corridors in North America, the Tintina Gold Belt. This is not scattered prospectors panning river gravel. It is industrial-scale wealth. Major operations such as the Fort Knox gold mine near Fairbanks and the Eagle gold mine in Yukon collectively produce over 500,000 ounces of gold every year, representing well over $1 billion annually at modern prices. And this wealth was not random. When the fault was active millions of years ago, it fractured the crust deeply, allowing hot, mineral-rich fluids to rise from below. As those fluids cooled within cracks and shear zones, gold crystallized and became trapped in the rock. Over time, erosion exposed those deposits, and humans eventually found them. This geological engine ultimately fed one of the most famous gold rushes in history, the Klondike Gold Rush. In 1896, gold was discovered in creeks feeding the Klondike River, and within months, word spread across North America. Thousands of prospectors surged into Yukon in a desperate race for fortune. They sifted icy gravels for flakes and nuggets, unaware that their riches had originated from deep, fault-linked hard rock deposits forged millions of years earlier by tectonic forces beneath their feet. Since then, the broader belt has yielded millions of ounces of gold, reshaping regional economies and fueling legendary booms. Entire communities owe their existence to this tectonic system. Even today, exploration continues along its structural trends, with advanced drilling and geophysical surveys targeting new discoveries. The implication is staggering. This fault did not just shift continents, it engineered a billion-dollar gold province. The same fault that built billions in gold can take it all away instantly. If a significant segment of the Tintina Fault were to reactivate, the consequences could be serious. A strike-slip fault stretching hundreds of kilometers has the theoretical capacity to generate a magnitude 7 or greater earthquake, depending on rupture length and stress conditions. While it would not rival the magnitude 9 megathrust earthquakes of southern Alaska, it could still produce strong regional shaking. Communities such as Fairbanks, home to nearly 100,000 people in the greater area, along with smaller towns across Yukon and interior Alaska, lie within reach of this fault system. Gold mines along the Tintina Gold Belt employ thousands of workers, many stationed at remote sites. Roads, pipelines, processing plants, tailings facilities, and power infrastructure could all be disrupted by intense shaking or secondary hazards like landslides. Permafrost adds another layer of complexity. In northern regions, frozen ground provides structural stability. Strong shaking could destabilize thaw-sensitive slopes, affect foundations, and alter drainage patterns. River systems could experience temporary blockages or shifts if landslides occur. In a worst-case scenario, collapsing infrastructure, slope failures, or industrial accidents could result in serious injuries or fatalities, potentially impacting tens of thousands of residents in interior Alaska and the Yukon, along with several thousand workers at remote mining and industrial sites, where emergency response times are long and medical facilities are limited. In remote regions where infrastructure is sparse and distances are vast, even moderate damage can have outsized impacts. That said, current scientific evidence suggests the Tintina Fault is not building strain like major plate boundaries, and no large rupture appears imminent. Its hazard is far lower than southern Alaska's subduction zone. Still, ancient faults don't disappear. The Tintina may never move as it once did, but it remains a permanent part of the North's seismic landscape. Seismic monitoring across Alaska and the Yukon is carried out by national geological agencies using networks of seismometers that record earthquakes and help map subsurface structures. GPS stations track millimeter-scale crustal movement, while geological mapping and mineral exploration drilling provide further insight into the Tintina Fault structure and history. Mining companies along the Tintina Gold Belt also invest in geotechnical monitoring, assessing slope stability, ground conditions, and seismic risks as part of operational planning. Key infrastructure, including pipelines and processing facilities, is designed with regional hazard levels in mind. Ongoing scientific research continues to refine understanding of the fault through rock studies, isotopic dating, structural reconstruction, and deep geophysical imaging. Remoteness remains a major challenge. Harsh climate, vast distances, and limited access complicate monitoring and emergency response. while climate change and thawing permafrost add new uncertainties. Preparedness here focuses on resilience rather than constant alarm. By understanding the geological framework, communities and industries can plan for low probability but potentially significant events. The Tintina Fault is being watched patiently and carefully. The Tintina Fault is a paradox, ancient yet structurally alive. It once shifted crust by hundreds of kilometers, rearranged mountain belts, and created pathways for gold that transformed the North. Today, it lies quiet beneath forests and frozen valleys. Its legacy is written in tectonic displacement and mineral wealth. Without its deep fractures and hydrothermal systems, the Tintina Gold Belt might not exist, and northern gold history would look very different. Seismically, it is not among North America's most dangerous faults, and its era of major movement has likely passed. Yet faults are not erased by time. They remain zones of weakness within the crust. Tintina reminds us that tectonic forces can both destroy and create. Beneath the wilderness stretches a 1,000-kilometer scar, silent for now, but permanently etched into the continent.